Hello everyone, welcome to the video lecture series on computer organization and architecture. So today's topic is speed up in parallel computing. So what is parallel computing? When one task is distributed into small fragments and the small fragments are executed parallelly. So this is called parallel computing. So when I have a single core processor, then my goal is to run a program faster. So normally we add more processor or cores. So from single core, the system may be upgraded to dual core, quad core, and so on. But the question is, even if I increase the number of cores in a processor, are all parts move faster with this modification? The answer is no. Because in any program, there are some parts, those are sequential, and some parts, those are parallel. So sequential parts means even if I add some processor to execute the task parallelly, the nature of the program execution is sequential. So even if there are more number of processors, so at a time only a single processor will execute that. But if some portions are parallel, just like it is shown in this diagram, that these blocks are appearing one after another, so these are sequential process. But these blocks, if you look at this, so two blocks are appearing in parallel. Okay, so these blocks can be executed parallelly. So the essence of this discussion is that even if we increase the number of cores in a processor, based on the nature of the code, the sequential part will not be benefited by more number of processors or addition of processors. Only the part that is sequentially programmed, this part will benefit from this addition of more number of processors. In 1967, Jean M. Amdahl observed this event, and he proposed a law to describe the theoretical maximum speed up achievable, because always there will be some limitation of the speed up, and due to that we need to plan the computer organization more effectively. So he proposed a law to describe the maximum theoretical maximum speed that is achievable even if we add several number of processors in parallel. So what does this law tell? So the first assumption of this law is that whenever some program is getting executed, so there will be some serial portion of the program and there will be some parallel portion of the program. So whenever we program anything, so due to the nature of the programming or nature of the utilization of resource, so there will be some serial portion and there will be some parallel portion. So if the f is the fraction of a program that is parallelizable, it means what? Suppose the total program is say 100%. Okay, so say for example I am telling that out of this 100%, 60% it's parallelly uh, s- it can contribute to some speed up. Okay, so 60% program is like parallelizable program, and third then 40% is the serial program, definitely if the total number of total portion is 100%. Okay, so Amadal called this parallel portion as f. Okay, so for example suppose this is 60%, now definitely 40% will be the serial portion, so definitely this is 1 minus f. Okay, now here I have expressed this as percent, but actually parallel portion means This is generally expressed as f is equal to 0.6 for example, and f is equal to 0.4. So same thing, that is just this is expressed as a fraction anyways. So and n are the number of processors, because my goal is to achieve some speed up by adding some number of processors. So n is that number of processors, and t means the total execution time on one processor. So in this diagram, this is a diagram for the time taken by a single processor. So there is a program, so total program is 1, that is a 1 portion, and the parallel portion is 0.6 for example, and then the serial portion is 0.4. Now if the parallel portion fraction is 0.6, so that is expressed as f. So what is the time involved in execution of this? That is naturally ft, because if t is the total time, then f into t, that is the time that will be taken by the parallel portion. So naturally 1 minus f into t, that will be the time taken for this serial portion. So now if I add these two parts, so if I add these two parts, so it will be like that: t is equal to 1 minus f into t plus f into t. And this is correct assumption, because if you expand this, so definitely it will be um, t minus ft plus ft. So ultimately see, we are getting t only. So anyways, so this expression is correct. So the basis of Amadel's law is actually this expression, that whenever we will be executing any program using any processor, there will be some parallel portion, there will be some serial portion, and accordingly the total time can be calculated. So that was all about the single processor. Now let us come to the next important part. So we have already assumed that n is the number of processor. So if I go back to the first diagram, so what we learned, that the effect of parallel computing is only on the parallel part of the program. It does not affect the sequential part of the program. So if I use n number of processors, so the performance improvement or speed reduction will only be applicable to the parallel part, not the serial part. So that is why with a single processor, if you look at this, with a single processor, if ft was the time, okay, this part is parallelizable, but there was only a single processor, so that is why the total time was ft. Now if I can distribute this time by n processor, because now I have used n processor, so this n processor will distribute the task among them. So definitely, as n processor will work simultaneously, so the effective time for executing this parallel part will be reduced to ft to ft by n. This reduction will take place definitely, because we are using n number of processors, and n number of processors are working in parallel. So for multiple processor or n number of processor, now what is the total time? So see, for single processor also, this serial part was 1 minus f into t, and for this multiple processor also, this serial part remains constant. It has no change here. Why? Because this part cannot be made this task cannot be made distributed. Okay, but this part of task could be distributed. That is why from ft2 this was reduced to ft by n. So now using multiple processors, what is the total time? So the total time that can be expressed as Tn. So Tn is equal to 1 minus f into t, that is the serial part, plus ft by n. Okay. So earlier it was we using a single processor, t is equal to 1 minus f into t plus ft. Now after I incorporated n number of processors in parallel, so this is the time for the parallel computing. Okay, so one important observation is that only the parallel portion becomes faster. Okay, the serial portions, the time for serial portions remains unchanged. The reason is already explained that why it happens. So now only the parallel portions could be made faster, and that is why the time taken has become less. So time taken has become less. It means that the speed has increased. Okay, so whenever there is some speed, I mean, that has increased, it means what? We have achieved some speed up. Now there is one parameter to quantify speed up, and that is directly called speed up parameter in Amadel's law. The speed up can be defined as very simple, that is speed after enhancement divided by speed before enhancement. So if I can find out the ratio, then we can understand that what is the current speed, or like 2x, 3x, 4x, like that. Now we know that the speed is always inverse to time. Why is it so? Because suppose one car travels from one place to another place. Suppose two cars are there. Suppose A and B are two places. So suppose one car travels from A to B. Its speed is say 10 kilometer per hour, and another car, suppose this is 20 kilometer per hour. So definitely what? For this car the speed is more. So speed is more means time is less, and for this 10 kilometer per hour for this car the speed is less. So speed is less means time is more. So with this basic understanding, we can get the idea that speed is inversely proportional to time. Okay, so it's a easy concept. So speed up, if it is defined in terms of time, so this after and before just alters, because this is reciprocal. So execution time before enhancement divided by execution time after enhancement. Okay, so speed after divided by speed before is equal to time before divided by time after. So this you need to remember. So anyways, so now uh, till now we have expressed all our performance parameters in terms of time. So we have the expressions for time before and after. So we simply put these expressions. So what happens? So time before enhancement means the process is serial or parallel. The process is serial. It means a single processor is used. Okay. So time before enhancement. So when single processor is used, so if I place that time, that is the time before improvement. And what is the execution time after enhancement? So after enhancement means when I placed multiple processor, okay, to achieve some speed. So if I make this two ratio, Okay, so final expression becomes the speed up is equal to 1 by 1 minus f plus f by n. This expression we get. This expression is known as Amdahl's law. Okay, so Amdahl's law, if I express in word, then this is the maximum improvement from parallel processing, and that is limited by the fraction of the program that must execute serially. So if you see that this 1 minus f, this term still remains here. So what is 1 minus f? 1 minus f is nothing but the serial portion of the program that we assume in the beginning, that if f is the fraction of the program that is parallelizable, so a1 minus f is the fraction that must remain serial. Now, what can I understand from this expression of speed up? So if the value of f and n are known, so definitely we will get some value for speed up. So if by replacing the substituting the values of f and n, so if the ultimate value is greater than 1, so it means that the performance is improved. So we got some speed up. So for example, suppose speed up is 4, it means that the program runs 4 times faster after the incorporation of parallel processors. If the speed up value is equal to 1, it means even after incorporation of parallel processors, there is no change in speed. And if we get the speed of value less than 1, it means the performance has become further worse even if we have used multiple processors. Okay, so when the values of f and n will be given, so from that we can calculate the speed up, and based on the value that we obtained as speed up, so we can have 3 types of interpretation. Now the question is, what is the maximum possible speed up, or can I add any number of processor to increase my computer speed, and what is the idea that how many processor I can add actually? So from that the idea of maximum possible speed up comes. So we assume that to increase the speed in an enormous way, so we include infinite number of processors in our system. Okay, so infinite number of processors means n is equal to infinity or tends to infinity. I mean, the number of processors are so huge, so lots of processors we have incorporated in the system that it is infinite. We assume that theoretically. So now in the expression in the of Amdahl's law, that is Sn is equal to 1 by 1 minus f plus f by n, in this expression, if I simply substitute the value of n with infinity, so definitely we will get 1 divided by 1 minus f plus f by infinity. Now what we know that 1 by infinity means 0. Okay, so this f by infinity, this part is becoming 0, then completely 0, and the final maximum speed up is becoming 1 divided by 1 minus f. Again this 1 minus f, this term comes. So the maximum possible speed up, it means when we are incorporating infinite number of processors in a system, in that moment also the maximum possible speed up is limited by the serial or sequential portion of the program. Okay, so the maximum possible speed up entirely depends upon the serial fraction of the program. So it means what? So we know that from this expression that maximum possible speed up S max is equal to 1 divided by 1 minus f. So that we know already. So now if f is I, f is what? F is the parallel portion, 1 minus f is the sequential portion. So F is high means the most portion or the majority of the programs or codes are capable to run in parallel. Okay, so if F is high, it means 1 minus F is low, it means the serial fraction is low, it means the maximum possible speed up is more. And if F is low means the parallelizable portion is low. So it means what? The serial portion or sequential portion is more. So as the sequential portion is more, so the maximum possible speed up will be less. Okay, and one important lesson that we have learned here, that even n is infinite, the speed up is not unlimited. Speed up is limited by the serial part. If you look at this diagram, so here we have plotted the execution time versus number of cores in a system. So suppose when we are using a single core processor, so there is some significant amount of parallel portion and some sequential portion. So this visual representation actually gives the clear idea that whenever I am increasing the number of cores, you see the parallel portion that is getting shorter. This is getting shorter, further it is getting shorter, but this portion remains same. These execution times remain same. And when this parallel portion is actually, this task is minimized by some infinite number of processor, so the parallel portion is very small, it is almost zero, but still the sequential portion exists. Okay, so the sequential portion does not go away. This is the big lesson of the Amadel's law, and it does not get smaller also. Okay, so even if you add up more number of processor, the sequential portion actually gets dominant more. From this graph, we visualize one interesting fact. Suppose the parallel portion say that is 90%. So 90% of the program is parallel. So 90% of the programming is parallel means it is more able to distribute tasks among the processors. So in this case, if you increase the number of processor, so you can achieve some good speed up. Okay, but after some time there is no improvement in speed up. Suppose the parallel portion is 90%. If the parallel portion is 90%, now see, compared to this 95%, this performance is significantly worse. Okay, so if suppose for the first case where the 95% program was parallel, so for example, when the number of processor was 4096, so from this point the performance remained unchanged. I mean, there is no improvement in the um, programming speed, execution speed. But for this 90% case, when this is 1024, from that itself there is no improvement. Okay, and the performance further becomes worse when this portion of this parallel part becomes smaller. So this is one significant observation from Amadel's law, that if I keep the parallel portion more, then the possibility of speed up is also more. If I keep the parallel portion less, the ability of speed up, that also becomes very less. Okay, so it is not about only the number of processors or what resource that I use. The main thing is programmatically whether we can achieve the parallelism. Okay, so that the task can be distributed, whether the system is able to distribute the task, that is more important. Now what is efficiency in parallel computing? So efficiency is nothing but the speed up that we have calculated just now divided by the number of processors that we use. So this is termed as efficiency. So efficiency is speed up divided by number of processor. What is the meaning of this? So efficiency indicates that how close the system is to ideal parallel performance. So for an ideal case, the speed up equals to the number of processor, or the efficiency is 1 or 100%. If efficiency is less than 1, it means some processors are remaining idle. Okay. If the efficiency is greater than 1, it means that is an impossible case, which is not possible. So if I get in any problem that efficiency is greater than 1, always assume that your solution has some problems. Okay. So let us take a small example that speed up is 6, that is given, and the number of processors are 8. So what is the efficiency? Efficiency is, so 6 by 8 is equal to 0.75 or 75%. So this is the result of my efficiency. Okay. So what we learned so far? So we learned, first we learned, before going to the next part, let's do a quick recap, then we will move. So first we learned that whenever some multiple processes are getting implemented, so we need to first check that what is the ability of the program to handle those parallel tasks. If there are no parallelizable part, then there is no use of many numbers of processors, because there are some serial portion, there is some parallel portion. Based on the parallel portion and serial portion, we get the speed up, that is the statement of Amadel's law. Okay, so Amadel's law say that the performance, this parallel computing actually is limited by the fraction of the program that executes serially. Now from this concept, we also obtain the maximum possible speed up, that if I increase the number of processors to infinite, then what will be my speed up? So that is 1 by 1 minus f. And then finally we got the idea of efficiency. So efficiency is nothing but the speed up divided by number of processors. So let us have a quick look on the differences of speed up and efficiency. So speed up means the overall performance improvement, and efficiency means how well the processors are utilized. So as per this definition, so speed up is old time divided by new time, and efficiency is equal to speed up divided by number of processes. So this value range can be greater than 1, and this is always less than equal to 1. So the speed up depends on the improvement in execution time, but the efficiency depends on the number of processors used. So speed up tells us that how much faster the program runs, and efficiency tells us that how parallel resources are utilized. Speed up, if we get the higher value, it means better performance, lower value means poor performance. For efficiency also, the higher value means the better processor usage. Now let us look at some numerical problems. So it is given that a program spends 40% of its execution time performing some floating point calculations. Okay, a new hardware design makes the floating point unit k times faster. Using Amadel's law, find the overall speed up of the entire program. Now, it's important to note that this floating point unit, or that is mentioned here, so some improvement could be achieved here. Okay, so some improvement could be achieved. It's more achieved. It means what? This is a parallel portion. So this is the parallel portion. Okay, so step one will be that as the parallel portion or floating point part is f is equal to 0.4, so the serial part is 0.6, and the improvement factor k means actually k is the number of processors. So parallel portion is improved by k factors. It means that this is actually the number of processors. So now if I apply Amadel's law, so the overall speed up is 1 divided by 1 minus f plus f by k. So if you substitute the value, so we get a expression that s is equal to 1 divided by 0.6 plus 0.4 divided by k. Now in the question, if k is given, then directly you can get a numerical value of speed up. Now let us look at the second problem, that a program has 90% of its work parallelizable and 10% must run serially. So clearly it is mentioned that f, that is parallelizable, it means f is equal to 0.9. So then 1 minus f is 1 minus 0.9, definitely this is 0.1 or 10%. I want an overall speed of 5x. Overall speed of 5x means actually the speed of value is given as 5. How many processors are required? So in this way, already you have the idea that how to do that. Speed up is 5. So 5 is equal to 1 divided by 0.1, that is the 1 minus f, and f is 0.9. Okay, so we get this equation first. Now we will solve for n, and n is 9. So n is 9 processes. Now if I ask you that what is the efficiency of the system, so definitely efficiency is equal to speed up divided by 9, speed up divided by n, because 9 numbers of processors are there. So if I substitute, then e becomes, or efficiency becomes 0.556 or 55.6%. So this is the efficiency value that we can obtain finally. So this was all about the speed up, the efficiency, Amadel's law, and how in different scenarios this Amadel's law becomes useful for handling parallel computing problems. Thank you so much for attending the session.